Hello and welcome to this revision session for AQA A-Level Physics, where we're going to be looking at magnetic flux linkage, which is part of the magnetic fields topic. So in this session we're going to look at three different types of questions. The first type of question is going to be on general check, so that will be on the basic questions designed to probe your understanding of the key concepts of the topic. The second set of questions are checkpoint questions, which are the more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. And then finally, our assessment point questions, which are the past paper examination questions which will mimic the types of questions found in public examinations. So let's have a look at these questions for magnetic flux linkage. So the first question say, a conducting circular loop of radius 0.250 meters is placed in the xy plane in a uniform magnetic field of 0.360 teslas that points in the same direction as the normal to the plane. Calculate the magnetic flux through the loop. Suppose the loop is rotated clockwise around the x-axis, so the normal direction now points at 45 degrees angle. Recalculate the magnetic flux through the loop, and then what is the change in flux due to the rotation of the loop? Then Argentina has more land area than Greenland. Why is the magnetic flux of the Earth's magnetic field larger through Greenland than through Argentina? So pause the video now, then unpause the video when you want to go through your answer. Right, so to calculate magnetic flux, you've got to remember that it equals BA, the magnetic flux density times by the area. Now, because it's a circular loop, we know that the area is pi r squared, so we pop in all our values, work it through, and we get our answer to be 7.1 times 10 to the minus 2 Webers. In our next question, really the flux links to the angle with the equation magnetic flux is equal to BA cos theta. So again now we'll take our value for B and A. Remember, A is going to be pi r squared. We then multiply it by cos 45, so we get 5 times 10 to the minus 2 Webers. So what is the change in flux? Well, you find the difference in the two values, which is 2.1 times 10 to the minus 2 Webers. Now for the second question, Greenland is a lot closer to the magnetic pole than Argentina, so therefore the magnetic field is going to be stronger there. Now that in itself isn't sufficient to conclude that the magnetic flux is greater, but Greenland's proximity to the pole also means that the angle the magnetic field lines make with the vertical is going to be smaller than that of Argentina's, and remember, the flux is equal to BA cos theta. So as a result, more field lines will penetrate the surface in Greenland, despite Argentina having a slightly larger area. The next question says, a magnetic field of strength 0.30 teslas is directed perpendicular to a planar circular loop of wire of radius 25 centimeters. Find the magnetic flux through the area enclosed by this loop. Find the flux of the Earth's magnetic field of magnitude 5.00 times 10 to the minus 5 teslas through a square loop of area 20.0 centimeters squared. When the field is perpendicular to the plane of the loop, when the field makes a 30-degree angle with the normal to the plane of the loop, and when the field makes a 90-degree angle with the normal to the plane. Then, a square loop of 2.00 meters on a side is placed in the magnetic field of magnitude 0.300 teslas. If the field makes an angle of 50 degrees with the normal to the plane of the loop, find the magnetic flux through the loop. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one we know that flux is equal to BA, so it equals B pi r squared. Pop in all our values and we get 5.8 times 10 to the minus 2 Webers. In our next question, when it's perpendicular, we don't need to consider cos theta, so phi equals BA, so you get 1 times 10 to the minus 7 Webers. Now, when it's at a 30-degree angle, you need to consider that angle by timesing it by cos 30, so it's 8.7 times 10 to the minus 8 Webers. And then here, when it's cos 90, well, cos 90 equals 0, so anything multiplied by 0 equals 0, so it's a value of 0 Webers. Now in question 3, we know that the magnetic flux phi is equal to BA cos theta. So it's 0.3 times by 2 times by 2, because it's a square loop, times by cos 50, so it's 0.77 Webers. The next question says, if a bar magnet causes a magnetic field with flux density of 20 milliteslas perpendicular to the plane of area A, how much flux will be contained by this area if it is 10 centimeters squared? A uniform magnetic field has a flux density of 5 times 10 to the minus 5 teslas and has an angle of 75 degrees to the region of area A. How much flux will be contained by this area if it's 1 centimeter squared? And then Zora takes a wire and winds it into a coil of 10 circular turns with a radius of 5 centimeters and then holds it in a magnetic field with a strength of 20 milliteslas. What is a magnetic flux linkage? So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, we know that flux linkage is equal to BA, so it is equal to 20 times 10 to the minus 3 milliteslas into teslas, times by 10 to the minus 4 centimeters squared into meters squared, so it's 2 times 10 to the minus 5 Webers. In our second question, it equals BA cos theta, so again it's 5 times 10 to the minus 5 times by 1 times 10 to the minus 4, because it's centimeters squared into meters squared, times by cos 75, so we get 1.29 times 10 to the minus 9 Webers. And in our third question, we're now looking at flux linkage. Now, flux linkage is equal to BAN cos theta. So we now know that n in this question is going to be 10. We know that the area is going to be pi r squared. So we then have to convert our 5 centimeters into meters. We work this all through and we get 1.6 times 10 to the minus 3 Weber turns. The next question says, in Britain, the Earth's magnetic flux density is 50,000 nanoteslas with the field approximately at the horizontal. Firstly, estimate the flux passing through your body if you stand vertically and are facing north. Then a typical smartphone compass uses a small magnometer chip to determine which way the phone is facing. Such chips are typically 2mm by 2mm squares. If you held a smartphone so that the magnometer chip was at an angle of 20 degrees to the horizontal, what would the flux passing through the chip in the phone be? Then in an electrical motor, a permanent magnet of flux density 18.4 milliteslas has its field placed perpendicular to a coil of 250 turns of copper wire. The diameter of the coil is 8.50 centimeters. What is the flux linkage between the field and the coil? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to estimate key values. So you can estimate the area of your body is about 2 meters times by half a meter by height times by your width. So it's about 1 meter squared. So therefore we could say thigh equals BA, so it equals 50,000 times by 10 to the minus 9 nanoteslas into teslas times by 1 meter squared, and it's 5 times 10 to the minus 5 Webers. The next question says, when we're looking through here, that thigh equals BA cos theta, so we can work it all through. Remember, we're square now, so it's 2 times 10 to the minus 3 times by 2 times 10 to the minus 3, so it's 6.8 times 10 to the minus 11 Webers. In our next question here, we know that the flux linkage is BAN cos theta, so it's 250 n times by our B, which is 18.4 times 10 to the minus 3, times by our area, which is pi r squared, times by cos theta, so therefore it equals 0.0216 Weber turns. The next question says, the figure shows a solenoid with a cross-sectional area of 0.10 meters squared. It is linked by the magnetic field of flux density 2 times 10 to the minus 3 teslas and has 250 turns. Calculate the magnetic flux and the flux linkage for this solenoid. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we know what our value for B is. We know B is 2 times 10 to the minus 3 teslas. The area is 0.10 meters squared. The angle is 0 and n is 250 turns. So magnetic flux is 2 times by 10 to the minus 3 times by 0.1. So it's 2 times 10 to the minus 4 Webers. The flux linkage is that value times by n. So you times by 250, it's 5 times 10 to the minus 2 Weber turns. The next question says, a bar magnet produces a uniform flux density of 0.15 teslas at the surface of its north pole. The pole measures 1 centimeter times by 1.5 centimeters. Calculate the magnetic flux at this pole. A solenoid has a diameter of 5.0 centimeters and a length of 25 centimeters. There are 200 turns of the wire. A current of 2 amps creates a magnetic field of flux density 2 times 10 to the minus 5 teslas through the core of this solenoid. Calculate the magnetic flux linkage for this solenoid, and a rectangular coil 5 centimeters times by 7.5 centimeters and having 150 turns is at right angles to a magnetic field of flux density 1.2 teslas. Calculate the magnetic flux linkage for this coil. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know flux is equal to BA, so remember it's 0.01 centimeters into meters times by 0.015 times by 0.15 is equal to 2.3 times 10 to the minus 5 Webers. Flux linkage is BAN, so therefore we know A is going to be pi r squared or pi d squared over 4. We can pop all the values in. Now again, remember, centimeters turns into meters in both cases, so we get out 7.9 times 10 to the minus 6 Weber turns. And in this next question again, flux linkage is BAN, so therefore it's 120 times by 1.2 times by 0.05 times by 0.075, centimeters into meters, so it's 0.54 Weber turns. The next question says, calculate the magnetic flux passing through a small circular coil of diameter 1.5 centimeters positioned between the poles of two slab magnets, given that the magnetic flux density between the magnetic poles is 300 milliteslas. Then calculate the magnetic flux passing through a circular coil diameter 2 centimeters if the magnetic flux density is 150 milliteslas and the angle between the normal to the plane of the coil and the direction of the magnetic field is 40 degrees. Calculate the magnetic flux linkage through a 20-turn circular coil, given that the magnetic flux density is 150 milliteslas, the angle between the normal to the plane of the coil and the direction of the magnetic field is 16 degrees, and the radius of the coil is 5.0 millimeters. Then determine the magnetic flux and the magnetic flux linkage through a rectangular coil of dimensions 5 centimeters times by 3 centimeters, given as 100 turns, a magnetic flux density of 120 milliteslas, and the angle between the coil and the magnetic field direction is 30 degrees. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, flux equal BA. We know A is pi r squared, so remember half our diameter of 1.5 centimeters, turn it into meters, and we can then pop it in the equation, so we get 5.3 times 10 to the minus 5 Webers. In our next question is BA cos theta now. So again, we need to work out our area, which is pi r squared. So we half our diameter to get our radius, convert centimeters into meters. So we then work it all through and we get our answer to be 3.6 times 10 to the minus 5 Webers. Our flux linkage is BAN cos theta. So once again, we convert our milliteslas into teslas, 150 times 10 to the minus 3. We've got cos 16 in our angle, and we've got our area to be pi r squared. Now again, we have been given, if you look in the question, a radius, so that's fine, but it's in millimeters, so we need to turn it to meters, so it's 5 times 10 to the minus 3. So our answer is 2.3 times 10 to the minus 4 Weber turns. And then in this next question, the flux is equal to BA cos theta. So you can work it all through. Now again, remember, it's a rectangular coil, so you'll times the two dimensions in meters. So it's 0.05 times by 0.03 to get our area. So you get 1.6 times 10 to the minus 4 Webers. And then our flux linkage is that value times by n. So you multiply that by 100, the number of turns, to be 1.6 times 10 to the minus 2 Weber turns. The next question says, state the SI units for magnetic flux, flux density and flux linkage. A single loop of wire coil has a cross-sectional area of 1.4 times 10 to the minus 4 meters squared. Calculate the maximum magnetic flux loop for this loop in a field of flux density 0.02 teslas. Calculate the magnetic flux linkage for the coil shown in the diagram. Then the direction of the magnetic field is reversed for the coil. Calculate the change in magnetic flux linkage. Then in London, the Earth's magnetic field makes an angle of 66 degrees with the horizontal and has a flux density of 4.9 times 10 to the minus 5 teslas. Estimate the magnetic flux for a small coin lying on the flat ground in Buckingham Palace. So pause the video now, then unpause the video when you want to go through your answers. Right, in our first one, magnetic flux density is measured in teslas, magnetic flux is measured in Webers, and flux linkage is measured in Weber turns. Note the difference between the three. In terms of magnetic flux, it equals BA cos theta. So we've got B, we've got A, and we've got our angle of cos to be 0. So therefore, that's our maximum value because cos 0 equals 1. So therefore, it's 2.8 times 10 to the minus 6 Webers. In this next question, we know magnetic flux linkage is BAN cos theta. So it's 400 times by 0.2 times by cos 30 times by pi r squared. So we work it through, remember centimeters into meters, to be 4.3 times 10 to the minus 2 Weber turns. Now, the change in magnetic flux linkage is that it's going to be double the difference because it's going to go from a positive value to the same value but a negative, so that's then a double of the positive value. So therefore the change in magnetic flux is going to be 2.14 times 10 to the minus 4 Webers, multiplied by n to get our change in magnetic flux linkage, so it's 8.6 times 10 to the minus 2 Weber turns. We can estimate that the radius of a coin is about 1 centimeter, so the area of the coin is going to be pi r squared because it's a circle. But remember, we convert our centimeters into meters, so it's pi times by 0.01 squared. Pop in all the values. Remember, the angle is 24 degrees, so it's 1.41 times 10 to the minus 8 Weber turns. The next question says, a rectangular coil rotates at a constant angular velocity within a uniform magnetic field of 0.121 teslas. The coil has 70 turns and a cross-sectional area of 59 centimeters squared. The diagram shows the coil looking along the axis of rotation. So calculate the flux linkage of the coil when the angle is 23 degrees. Then as the coil rotates, explain what values of theta provide the maximum and minimum values of induced EMF. So pause the video now, then unpause the video when you want to go through your answer. Right, so our flux linkage is equal to BAN cos theta. So we have B, 0.121, we have N, 70, and we have cross-section area to be 59 times 10 to the minus 4, because centimetres squared into metres squared. So you got your angle to be cos 23, so we get 0.046 Weber turns. Now, when the angle is equal to 90 degrees, because you have your maximum change in flux linkage at that point, you'll get your maximum value of induced EMF. When the theta is equal to 0, you'll get no EMF because the flux is not being cut at all at that point. So the rate of change is 0, so the rate of the induced EMF will also be 0. Now in this last question, a square of sides with length 4.5 centimeters is placed in a magnetic field normal to the field's direction. Find the magnetic flux passing through the square if the magnetic flux density is 0.92 teslas. The flux linkage of a coil with a cross-sectional area of 0.33 meters squared normal to a magnetic field of flux density 0.15 teslas is 4 Weber turns. How many turns are in the coil? And then finally, a rectangular coil of 200 turns in size 5 centimeters and 6.51 centimeters is rotating in a magnetic field with a value of 8.56 times 10 to the minus 3 teslas. Find the flux linkage of the coil where normal to the area of the coil is 12.6 degrees to the magnetic field. So pause the video now, then unpause the video when you want to go through your answers. Right, in our first one, we know that the area is equal to 2.025 times 10 to the minus 3 meters squared, because the area is a square, so you've got to times the two dimensions together. Phi equals BA, so it equals times by 0.92. It's 1.863 times 10 to the minus 3, so therefore we can round it to be 1.9 times 10 to the minus 3 Weber turns. We know flux linkage is equal to BAN. So therefore, when we rearrange it through, N is equal to N phi over Bn. Now you can't cancel the N's through because you want to work out N, which is on the left-hand side. So it's 4 over 0.15 times by 0.33. So you get your answer out to be 81 turns. And then finally, in the last question, we know the area is equal to 5 times 10 to the minus 2 times by 6.51 times 10 to the minus 2, which is 3.255 times 10 to the minus 3 meters squared. We know the flux linkage is equal to BAN cos theta, so you can pop in your values. You got your value for A, which you just worked out. We're given the value for B in the question. We are given the value for N in the question. We know the angle is 12.6, so therefore we get our answer out to be 5.44 times 10 to the minus 3 Weber turns. So that brings us to the end of this revision session on magnetic flux linkage, which is part of the magnetic fields topic in AQA A-Level Physics. So thank you so much for watching and have a lovely day.